So today I will tell a little bit about the history of quantum computing, how it went from wild idea into which almost nobody believed to a major research topic that is being pursued by thousands of people worldwide. So then what can we do with quantum computer if and when we build one, and how far are we actually with building one? Yes, so quantum computing, as many of you probably already know, combines quantum physics and computer science. In short, it tries to use quantum effects to do computing and communication better. And the history of quantum computing starts with Richard Feynman, one of most famous physicists of 20th century. So in 1981, at the end of his career, he was invited to give an invited talk at some major international congress. Well, he could choose any topic to talk about, and he chose to ask the question, can we simulate physics on a computer? And it was a trick question because he knew that the answer was no. So he asked this question, and then he went on talking that physics involves quantum physics, and if we try to simulate quantum physics, we run into a problem because the full description of quantum mechanics has so many variables that it's infeasible to keep track of them all. So if we have a system of n particles, with each particle described by 2 variables, then the full quantum mechanical description would have 2 to the n variables to describe the whole system. And that just grows too quickly to keep track on any computer. If we have 100 particles, that's 2 to 100, that's 1 with 30 zeros. It's very dangerous to say that computers will never be able to do something, because those predictions get defeated again and again. But in this case, I think it's justifiable to say that computers will never have memory that stores 2 to 100 variables. And then this all was known at that time, but the really brilliant idea was what followed. Feynman asked, if we can't simulate quantum physics on a computer, maybe we could use quantum physics to build better computers. Maybe we could turn a problem into something positive. And yes, so what happened next? Immediately nothing happened. This idea was too unusual. The question was asked by the most famous physicist possible, but there was no clear starting point what to do next. Okay, so how would a quantum computer look like? How could we even try to solve something with it? So for next 12 years, not that much happened. There was a small number of physicists and computer scientists trying to figure this out, but this was a very small number. But eventually, the world got to something, and now we know that if we could build quantum computers, we could actually use them for quite a few things. The first one is something that was already guessed by Feynman. A quantum computer would be able to simulate quantum physics. Since it's natively quantum, this would be just simulating one quantum process with another quantum process, rather than trying to keep track of a quantum description on a classical computer. So, for example, we could describe chemical processes by Schrödinger's equation and solve it. And then we would be able to do quantum chemistry on a computer exactly without any approximations. And this is actually something quite important, because there are estimates that quantum chemistry takes about 10% of all supercomputer time now. So from this perspective, if it costs hundreds of millions to build quantum computers, there is actually a good chance that this money is well spent, because it probably 10% of supercomputer time is probably worth more than hundreds of millions. Now, what is much more surprising, and what was probably not obvious to Feynman, is that quantum computers can actually solve tasks that do not involve quantum mechanics in any obvious way. Well, the one very famous one about which many of you might have already heard is factoring large numbers. So let's say that we have a number that is a product of two smaller numbers, and we are given this large number, and we want to factor it into smaller numbers. Then this is a very well-known difficult task for conventional computers, and if it comes to numbers of 300 digits, well, ordinary computers can't do that. There is simply no good methods for that. On the other hand, if we could build a quantum computer, it would be able to factor large numbers efficiently. And then a lot of encryption and secure data transmission today is based on the promise that factoring hard numbers is hard. So someone who built quantum computers would be able to read a lot of encrypted information. Now, but this is a well-known story, so I will not stop too much on it. Rather, I would like to tell about other things that one could do with quantum computers, but are not so well known, but I think are still very interesting. And as a computer scientist, I will focus on things where quantum computers can be used to solve problems in conventional computer science. So it's problems which don't involve quantum mechanics in any way, but can be solved faster on a quantum computer. So here is one that is still well known. Not as well known as factoring, but still quite well known. So let's say that we have a general search problem that involves checking a large number of objects. And the operation that we can do is we can check whether a given object has the right property or not. We look at the object and see, well, this is the right one. So then the question is, how many such operations do we need to find an object with the right property? Now, on a conventional computer, if there are n objects, only one with the right property, it is quite obvious that it might take n steps to find the right object, because we might look at it last. It's something that is very obvious. Now, if we had a quantum computer, and if we were able to check these objects in a quantum superposition, we would be able to check them all in square root of n quantum steps. So for 1 million objects, that would be 1,000 steps instead of 1 million. And this is usually, in popular press, this is usually told as a story about searching a quantum phone book. So let's say that we have a phone book. This phone book is indexed by people's names. We want to do a reverse lookup. We want to know who has this phone number. Then the operation that we could do is we could look at all entries in this phone book and see, does this person have this phone number? Does that person have it? If the phone book has 1 million entries, it would take 1 million steps to find the person with this phone number. Now, if this was a quantum phone book stored in a memory of quantum computer, we would be able to do it with 1,000 steps instead of 1 million. And there are a few caveats in this story. The big caveat is that we would have to get this whole phone book into a quantum memory. So we would need a quantum computer with a memory that is large enough to store a phone book. Okay, so this is something that might be only possible in a very distant future. So when I talk to audience of professional computer scientists, I try to avoid this story because they would catch me. But quantum search can be useful for many other things. And its main use is actually in situations where this phone book is not something real, but is something virtual. So here is an example. So let's say that we want to solve some exhaustive search problem in which we want to examine a large number of possibilities. So one possible problem would be we are given a graph and we want to know whether it has a cycle that passes through every vertex exactly once. Well, in graph theory, this is called Hamiltonian cycle. And this is a very well-known difficult problem in computer science. And the difficulty comes from the fact that there are just too many possible cycles that might pass through all the vertices. If we are given one cycle, it's easy to see whether it works or not. But there are too many candidates. The number of candidates grows exponentially, just like the number of variables in a full description of quantum mechanics. Now, well, this is essentially a problem in which we have to check many possibilities. So we could do quantum search here. And we could solve this problem in time that is order square root of the number of candidates. So if we had to check 1 billion of cycles, we could do it in time that was square root of 1 billion. And the wonderful thing about this is that this is applicable to any search problem, no matter what's the nature of the search problem. We could be trying to break a secret cipher, and in code breaking, we often have to examine a large number of possible secret keys. Now, if we use quantum search to find the right secret key, we could do with examining square root of 1 billion keys instead of 1 billion. And in this way, we could break even crypto systems that are not based on factoring and that are not broken by quantum algorithm for factoring. So the short summary about quantum search is that we will probably never use it for searching phone books on a quantum computer. But we might use it to search for a cycle in a graph or to search for a secret key to break a cipher. Now, let me go on to a few more quantum algorithms. So these are all things that in which I have been somehow involved myself by contributing some part to them. And they are all much less known than the ones that I told you so far. So here is another computational task. We have a large array of numbers, and we want to find two equal numbers in this array. Okay, so this particular array has a lot of equal numbers, but if array was of size n, and it only had two equal numbers, it would take n steps for a conventional computer to find them, just because the two equal numbers might be the last one at which conventional computer looks. And even if we think of the number of steps that conventional computer would need on average it would have to look at about half of the n numbers before it runs across the two equal ones. Now, a quantum computer would be able to find two equal numbers in time that is roughly the size of this array to power 2/3. So that's 10,000 time steps instead of a 1 million. And here is another one. Let's say that we have a logic formula consisting of logical OR and AND gates. And we want to know to what this formula evaluates. And this formula is of size n. And this formula might be actually either an explicit formula given to us, or it might be something implicitly specified. For example, this formula might describe a winner in a tree consisting of positions in two-player game like chess. And so the question is, at how many, so the question is, at how many variables in this formula do we have to look to find out the value of this formula? Again, a conventional computer would probably have to look at all the variables. Okay, that's, well, okay, that's not completely right. A conventional computer might have to look at all the variables, at least for certain structures of formula. And a quantum computer, again, would be able to do in time that is square root of the size of the formula. And this algorithm is very cute. It is based on a nice physical analogy. So I will sketch you how this algorithm works on a very high level. Okay, so here is the formula. We represent this formula as a tree. Then we imagine that in the places where variables are 1, we attach an extra edge to this tree. And at the place where the result of the formula comes out, we attach a tail. And this structure exists in the memory of our computer. Whenever our computer has to examine this leaf, it checks whether variable is 1, and then, depending on that, attaches this extra edge or not. And then we simulate a quantum process in which we place a starting state on this graph, and the starting state is distributed on this tail according to a certain pattern. And then what happens is, if formula evaluates to 0, then the starting state stays essentially unchanged. We stay in this tail. If the formula evaluates to 1, the starting state goes and scatters into this tree. And well, when I saw this algorithm, it looked kind of magical to me. But there was this physical process. We would start this particle in this tail, and then it would either scatter into this tree or stay here, depending on whether formula was 0 or 1. And to see why this is magical, there are many different ways how formula could evaluate to 0. And there are many different ways how formula could evaluate to 1. And one would expect that these many ways would lead to different behavior, but they don't. All the cases when formula evaluates to 1 lead to this particle staying here. All the cases where formula evaluates to 1 lead to this particle scattering there. And the people who invented this algorithm, they actually had an intuition for that. They had an intuition in terms of reflection coefficient. They were thinking of this as a particle on line that encounters an obstacle and either passes through or gets reflected. And in those terms, it's actually quite natural. But when they told that to me, it sounded really magical. So here is another recent quantum algorithm. So this one was quite controversial and is still controversial. Let's say that we have a large system of linear equations and we want to solve it. We are given coefficients of this system of linear equations and we want to find the values for the unknowns. And well, this is a major task in scientific computing. It has been an object of a lot of research in computer science. Well, basically the conventional algorithms scale in time as some power of the number of variables. if we think about general systems of equations with not much constraints on coefficients, then that's number of variables to power 2.37. Okay, and then about 5 years ago, there was this quantum algorithm which made headlines in popular science press. So this is headline from Scientific American. New quantum algorithm can solve monster-size equations. Okay, so here we actually have a quantum algorithm that can solve systems of billions of equations in maybe 30 or 50 time steps, but with a few caveats. So here is what this algorithm does. It produces a quantum state which encodes a solution to the system of linear equations. And it produces this quantum state really quickly. The time for producing this quantum state scales as the logarithm of the number of equations. So logarithm of 1 billion would be 30. Now, the downside of this algorithm is that it produces a quantum. It doesn't give us the values of all the unknowns. It gives us a quantum state that encodes them. So then the big question about which we are still thinking is, what can we do with such a quantum state? We can't extract all the information from it, but it seems that we can do some things, that we can find some things about the values of unknowns that are hard to find conventionally. So for example, one thing that we could do is we could produce these quantum systems these quantum states for two systems of equations, and then we could measure whether these quantum states are similar or not. And then we would have a quantum algorithm for comparing whether solutions to two systems of equations are similar or not, which would work much faster than the time to solve these systems on a conventional computer. Okay, so now let me go on to a very popular description why are quantum computers better. So here is a way how I think about quantum computers. Well, I'm a computer scientist, and actually, I have never taken a quantum physics course. Well, after I got involved in quantum computing, I did read Feynman's lectures on physics, but I got involved into quantum computing without having ever taken quantum physics course. So the way computer scientists think of quantum computing is they think of quantum world as a generalization of the probabilistic world. So in a probabilistic world, we could be in one of several locations with certain probabilities. So from computer science perspective, quantum world replaces probabilities with amplitudes. So instead of probabilities summing up to 1, we have amplitudes whose squares sum up to 1. So yeah, so here's a nice quote from a computer scientist colleague of mine. What is quantum mechanics about? From my perspective, it's about information and probabilities and observables and how they relate to each other. And this is very much how I feel about the type of quantum mechanics that I do from quantum computing. It's something that abstracts away all the physical details and works on the level of amplitudes. And then on this level, the power of quantum computers comes from two effects, one of which is quantum parallelism. If we have a quantum state that involves a superposition over 1 million states, we could do 1 million computations on it. And we would get a quantum superposition over 1 million answers. Then the question is, what could we do with such a state? If we measured it, then out of these 1 million results, we will get just 1 million answers, just one answer. So we have a quantum state that encodes 1 million different answers, but we can only get out one. So the answer to this is quantum interference. This is my popular lecture slide. So let's say that we have two paths how we could get to a destination. And in a classical world, if on each of these paths we get to a destination with probability 1/4, then 1/4 plus 1/4 adds up to 1/2. Now, in the quantum world, quantum states could interfere one with another. So if we have two paths, and on these paths, the probability of getting to destination are 1/4, they could interfere, and 1/4 plus 1/4 could add up to 1. Because what we are actually adding up in quantum world are amplitudes. So many amplitudes which translate to small probabilities could add up to a big amplitude which translates to a large probabilities. And this is essentially how quantum computing works. We do this computation that produces a quantum state that involves in 1 million computation results, and then we somehow try to interfere them and produce a result that depends on all 1 million values. And the big challenge is to do this interference so that we get something meaningful that helps us to solve the problem. In case of factoring, we could do this huge amount of computation and then do interference so that we obtain something that is useful for factoring large numbers. For many other computational problems, we could do billions of things in parallel, but we don't know how to interfere them to obtain a result that is useful. And these are the problems for which we don't get quantum speedup. Okay, and now, well, in conclusion, let me tell about the current state of the art with building a quantum computer. So what do we need to build a quantum computer? Well, we need quantum bits, which are systems that can encode information, systems that can encode zeros or ones. And there are many different ways how we can encode a quantum bit. We can encode a quantum bit by an ion trapped in an ion trap. We can encode it by nuclear spin. We can encode it by an electron spin, and so on. So there are tens of different ways of possibly building a quantum computer. Essentially, quantum bit captures what is common to all of those physical systems. So in this sense, quantum physics is a meta-theory which describes all these physical systems. And then if we take out the information theoretic part of quantum physics, this is this thing that is common to all the physical systems. After you abstract away all the details, what you are left with are amplitudes, probabilities, and quantum bits. Okay, so, well, and the two technologies that have been the most successful so far are ion traps and superconductors. So in an ion trap, one uses a combination of electric and magnetic fields to capture individual ions. So one captures individual ions and in a vacuum and puts them in a precisely defined locations. And one can capture, say, 14 ions and arrange them on a line and shine a laser on them and compute on them in this way. So using an ion trap, one would encode 0 in the lowest energy state of an ion and 1 in the second lowest energy state of an ion. And then we have these 14 ions with 14 zeros and ones encoded, and we can shine a laser on them and manipulate their state and compute in that way. So here is how the device, how this looks in the laboratory. This device only has 14 quantum bits, but there is a lot of supporting equipment in it. And then the other possibility is superconductors. So in a superconductivity is a quantum effect. And in a superconductor, the whole electric current is in one quantum state, and this is what explains superconductivity. So then we can encode 0 by a current flowing in one direction and 1 by a current flowing in another direction. And here we have a quantum state that actually consists of many electrons, all of them being in an identical quantum state. And in superconductors, one can do quantum gates with precision 99-point-something%. So the individual elements for operating individual quantum bits are getting really reliable here. And one advantage of this technology is that these superconductor devices can be fabricated using the standard integrated circuit techniques. And this is something very important because, for example, in an ion trap, we have a lot of lasers, and these lasers have to be arranged for every quantum bit. So producing 300 quantum bits is 20 times as difficult as producing 15 quantum bits. And there is a question, will we ever be able to arrange all the equipment necessary for 300 quantum bits? Maybe, but it's not obvious. In superconductors, what we know is that we can fabricate them using standard circuit techniques. So if we manage to get a few basic things right, we can and go to, say, 20 or 50 quantum bits, we would probably be able to go to 1,000 or 10,000. And for this reason, quite a few experimentalists are getting quite optimistic about quantum computing. So we have high-quality components, and we have these high-quality components in technologies that allow mass manufacturing of them. So this gives a hope of building quantum computers in 15 to 20 years. Now, there are actually some predictions that have been even more optimistic, 10 years. There was even one prediction that predicted 2020. I would not go with the last one, but I think 15 to 20 years is possible. And yeah, this is a timeline of steps that one needs to go through to get to a quantum computer. Operations on single quantum bits, algorithms on multiple quantum bits, measurements for error correction and control. This is all done. Then the next step is quantum error correction. If we do a long computation, there will unavoidably be some errors. We can make components reliable to 99.9%. We will never be able to do 100%. So there needs to be some error correction that eliminates the remaining errors and produces quantum bits, encoded quantum bits, that are actually encoded in other quantum bits, which last longer than a real physical quantum bit would be able to last without an error correction. So this is the next step. Quantum bits that last indefinitely long based on quantum error correction. And then once one builds those, there would be a similar sequence of steps. Operations on encoded quantum bits, algorithms on multiple encoded quantum bits, fault-tolerant quantum computation. At the moment, we are in the middle of this 7-step timeline. It took the world about 15 to 20 years to do these 3.5 steps. It would probably take the same amount to do the remaining 3.5 steps. I don't bet on on experimentalists in the laboratory doing these remaining 3.5 steps sooner. Okay, and well, let me conclude with another nice quote from a computer scientist. So this was said by Alan Key, who is a famous computer scientist who invented some very well-known computer programming languages. What he said is that in natural science, nature has given us a world, and we are trying to figure out how it works. In computers, we can invent our laws, we can stuff our laws into a computer and make it work as we want. We can create a world for ourselves. So what quantum computing is doing is, I think, it's making quantum physics like computer science. It's inventing the laws that we want quantum particles to follow and challenging the physics world to build a quantum system that follows these laws. Okay, so that's all. Thanks.
Okay, so thank you very much for this talk, and on behalf of the organizers, I have a little present for you. But please stay for some question time.
Thank you.
Okay. So who has the simplest question? You.
I wonder, how's the readout of the results given by the mathematical readers and how the real numbers are obtained? For example, you showed the example of the system of linear equations, and at the end you have this superposition of states. How do I know the basis? Can I make a projection of this state on some state and just extract a single number of bases?
Well, okay, so in case of linear, well, basically you have to reduce the situation to a case when measuring when measuring the system in the standard basis gives you some information. In the case of system of linear equations, yes, the readout is a big challenge here. So what one could do is so this algorithm, so you won't be able to get the solution out of this algorithm. What you could do is you can find out whether solution is well correlated with a certain direction by measuring the correlation, by measuring the quantum state in this direction.
So basically this basis, 1 to n is unknown.
No, you know the basis 1 to n. You know this basis you can measure. If you measure in this basis, you get one of elements with probabilities that are amplitude squared. So if you measure in this basis, you might be able to tell which variable has the largest value. People are certainly thinking. There is a fair number of papers written about 3-level quantum systems and settings where they might be useful. And I actually have a paper about use of Q-trees for quantum cryptography, and there is a group which implemented this in a laboratory because they had a 3-level quantum system and they wanted something where 3-level quantum system does better than 2-level quantum system, so they implemented my cryptographic protocol. Now, if we talk about general purpose computation, then if we use quantum bits, that gives us the biggest range of possible physical systems on which we can implement them. Like Q-trees, the number of, well, the range of physical systems would be smaller, it would get more specific. And with qubits, it's also, since we only have two levels for one system and 4 levels for pair of systems, the elementary operations are quite simple, and one could do with quite simple range of quantum gates. With Q-trees, again, it gets more difficult.
Thank you. More questions?
Yes?
And they choose 9 qubits. But what refutes their scaling further at the moment?
Well, okay, actually I don't know. I know that scaling is the next thing on which they are planning to work. So, but I don't know whether there has been some fundamental obstacle or whether they have just been trying to work on the precision before scaling it up.
Okay, so unless I'm not updated, I know that this company Keyway is selling quantum computers, but does anybody know what they are actually selling?
No. Okay, so, well, okay, we know that D-Wave claims to have 2,000 noisy quantum bits in their device. And the big question is, are there quantum effects? I think the conclusion is that there are certainly quantum effects on a local scale. Say if you take 4 or 8 neighboring quantum bits in D waves, there are certainly some quantum effects going on there. The unknown situation is if you take the whole 2,000 quantum bits and compare it to classical computation in an honest way, does it actually do anything better? So they have these experiments that have made all the press, but they can be hundreds of millions of times faster than classical computer. But these comparisons have typically been apples to oranges. So they take their machine, they compare it with a classical algorithm of completely different nature on a set of inputs that is very well suited to their algorithm and not suited to the classical algorithm. So the right comparison is that you take a classical algorithm that is run on a classical computer, but is most similar in nature to their algorithm, and you compare that with their algorithm. And in that comparison, they are not winning yet.
More questions? Actually, I have a few questions. One very general thing. Do you think it's more promising to try and build a really universal quantum computer or a quantum simulator for a specific task, such as factorization or linear equations or whatever? Because classical computers that we have, they are general. They are universal. They can run word processors, they can do computations. What about quantum computers?
Well, I think simulator might be more promising. Well, okay, I don't quite know yet. We are still at a sufficiently early stage, so it's difficult for me to predict. But I think simulator might be easier to build. And simulating quantum systems is something that might be easier than general purpose quantum computer.
Okay, and by the way, if there are no more questions from the audience, I would like to ask a somewhat specific question about one of the algorithms you presented. It was about finding 2 equal numbers in an array. If I tried to solve this problem thinking classically and using a classical computer, I would simply sort the array, and then I would see all the equal numbers sticking together. So is this problem of finding the equal numbers really different from the problem of sorting, or it's more or less the same thing?
Well, okay, so it's different from sorting in a sense that we don't know how to solve sorting on a quantum computer. The way how this algorithm works is that it keeps track of some subset of numbers in a quantum memory, sorting this subset, but it never has to sort the whole array. Now, if we wanted to do sorting faster on a quantum computer, meaning sorting the whole array, we essentially run into a problem. But if we want to output the whole array, well, what we are outputting is already as long as the array. So we need a classical number of operations just to output the whole array. So there's probably not much that one could gain by quantum computing.
Okay, thank you. One more question.
I was feeling that creating algorithms for quantum computers from completely different business from creation algorithms or mathematical algorithms. And it seems like the quantum algorithms are very unintuitive. Am I right? Or is it a problem?
It is. It is. we are working on it. We are working on it, but and it's probably easier than it was 20 years ago, but it's still a problem.
Is it a way to learn it, like, or you just want magic inside it to think of somehow?
Well, there is a usual way to learn how people learn many ways. They learn existing algorithms. There has been some body of research devoted to simplifying existing algorithms and putting them into form in which one could use them for solving other problems. So there is some bag of tricks that one could exploit. This bag of tricks is not empty, but it's still smaller than for conventional computers. So when I teach quantum algorithms to my students, what I often do is I try to phrase some of existing quantum algorithms as quantum black boxes that one could use without knowing anything else about quantum mechanics. And there are some things that one could do in this way. And hopefully there would be more such black boxed primitives that one could exploit.